Hi, in this video we'll start learning about trigonometric identities. Let's quickly remember a few facts. Now when we have an angle theta between the radius and the x-axis, right, we have this point P. Formerly it was x and y, right? The coordinates were x and y, but we found out that the x value is actually cosine theta and y value is sine theta. So we changed the coordinates to be cosine theta, sine theta. The idea here was to apply Pythagoras, right? And when we have the triangle, drawn here a little bit bigger, now we said that this is theta, the radius is 1, so this is sine theta and this length is cosine theta. The first trigonometric identity came out from Pythagoras. So cosine squared theta plus sine squared theta equals the hypotenuse squared, which is 1 squared, which is 1. Obviously, changing these, swapping these does not change anything. So you could also say sine squared theta plus cosine squared theta equals 1. Now from here, I could just take sine squared theta to the other side. So I could write cosine squared theta is 1 minus sine squared theta. Or instead, I could take cosine squared theta to the other side. So I could end up with sine squared theta equals 1 minus cosine squared theta. So I can manipulate this identity into two other expressions. So if I want to write down an equation in terms of sine only or in terms of cosine only, I can just change them into one another using these expressions, right? That's one thing. Second, if we just write down tangent theta, it's going to be, according to the angle theta here, opposite over adjacent, right? It's TOA. So I would go like sine theta over cosine theta. So this is my second identity. Now let's see some examples of how we use these identities in questions. So the first type could be simplifying expressions, like the first one. So if you just take 5 as a common factor out, so it's going to be 1 minus sine squared theta, which would then be 5 cosine squared theta, as this expression is nothing but cosine squared theta. And the second one, that's going to be sine of 2 theta over square root of cosine squared 2 theta, right? And if you have the square root and square, they cancel each other out. So you end up with sine 2 theta over cosine 2 theta, which will end up with tangent 2 theta. So basically, you will use these two identities to simplify expressions. Another example. Now, this is a proof question, and cosine to the power of 4 theta minus sine to the power of 4 theta must remind you something, must ring a bell. Now, you have to use in these expressions all of your algebraic skills. For example, you have to figure out that this is actually difference of squares at the top, and then you have to factorize accordingly. And when you factorize it, you'll see that this part is 1 because it's the identity, right? So you end up with cosine squared theta minus sine squared theta over cosine squared theta. Now, you could do either this, write these are separate fractions and end up with 1 here and tangent squared theta here. So you show the result there. Or you can try changing, for example, sine squared theta into 1 minus cosine squared theta and simply get stuck, ending up with something which seems totally different than what is asked. So not every single time that you change one trigonometric function to another will work. So you have to be really careful. Again, practice makes perfect. Given that cosine x equals minus 3 over 5 and x is reflex, find the value of sine x. Now there are two ways of approaching this question. One is algebraic, the other is geometric. I'll show both and you can pick any one you'd like. So the book shows the algebraic method, which is that you use sine squared x plus cosine squared x equals 1. So sine squared x will be 1 minus cosine squared x. Now you know cosine x, so you can just substitute it here. So you can say sine squared x is 1 minus 3 over 5 squared, right? From here you'll get sine squared x to be 1 minus 9 over 25, which will give you 16 over 25. So you can end up sine x being plus minus 4 over 5, right? So you have to now decide whether it's plus or minus. Now, the question says that the angle x is reflex. This means that the angle will be either in the third quadrant or the fourth quadrant. But just because, for example, it could be here like this, or it could be here like this. But just because in each of these quadrants sine x is negative, right? We can write sine x equals minus 4 over 5 with confidence. So that's the answer. Now in the geometric approach, we just use right triangle, right? And we try to set the numbers given in this ratio into this triangle. Now we're talking about cosine x, which means adjacent over hypotenuse. So ignoring the sine, this is 3, this is 5, I can say, right? So I can just go through 3 squared plus a squared is 5 squared, and from here I can find a to be 4, right? And from here I can directly write down sine x being 4 over 5 as opposite over hypotenuse, right? Now all I have to think about is this word. Reflex again means that the angle will be either in the third or the fourth quadrant, right? So in either case, sine x must be negative. So I'll go like sine x equals minus 4 over 5, right? This is very simple if you can just quickly figure out the side lengths with the Pythagoras. So it looks shorter, and yes, you use the idea of the angle given being reflex, or in other cases like obtuse, whatever, and then you just decide the sign of the value of sine x, all right? So you can use whichever approach you'd like while solving such questions. One quick note before I finish: you may have to use cosine rule and sine rule while solving trigonometric questions in P2 and P3 and P4 onwards. So it's building up on it. So don't think that the questions will not require any previous trigonometry knowledge, all right? Keep in mind that cosine rule and sine rule could be treated as identities that you may use as well, right? So that's pretty much it. That's how you play with trigonometric identities. And as always, practice makes perfect. Thanks for watching.